Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Kilopass with Bruce Bateman, who's going to address some of the issues of scaling of DRAM, which has become a problem as we start moving down to the more advanced process nodes. So Bruce, we've heard a lot about thyristors over the years. What exactly is a thyristor and what's the problem there?
A thyristor is a bipolar device that is a stack of a P layer, N layer, P layer, and another N layer. Schematically, it looks like a PNP bipolar device cross-coupled with an NPN type bipolar device. They've been around since the 1950s. They have a latching property. We see this in CMOS with the phenomenon called latch-up in CMOS, where it'll be either in an off state or latched into a very high conductive state. If we can confine this thyristor structure to a small physical geometry and isolate it from adjacent thyristors, then we can use them as individual elements for a memory cell.
And we've also been talking about bipolar for a long time. Bipolar has a reputation of being old, fat, and not very efficient. Has that changed? Is that still a problem?
It's not a problem if you operate the bipolar device in a new manner. The old style of bipolar devices always had constant current running through them, which increased the power dissipation in the chip. They were also mostly lateral along the surface of the device, which made them very large in terms of layout areas and non-competitive against CMOS. But now with advanced lithography, advanced shallow trench isolation and so on, we can fabricate thyristors in a purely vertical manner that makes them small compared to their competing MOS devices, and therefore they become very attractive as a memory cell.
So why don't you draw this out for us?
Okay.
So what are we looking at here?
So what I'm showing here is the basic thyristor and how it looks schematically and how it looks from an electrical point of view. Thyristor is just a stack of doped layers, P-type, N-type, P-type, and N-type. In a traditional bipolar structure, if I look at the PNP, that builds what we call the PNP structure, which is emitter, base, and collector on the PNP. If I look at the bottom half of this, I've got NPN, which is this NPN structure here, which is collector, base, and emitter. In this stack, what happens is this base region is the same as this collector region, namely this P region here. This base region and this collector region are the same region here, and so we end up with this cross-coupled bipolar structure. This exists in CMOS as what we commonly think of as latch-up. If I contain this to a unique device, then we get an electrical operation that looks like this. This is log of current versus voltage from the anode to the cathode. As I increase the voltage across the anode, initially this device is in what we call an off or blocking state and virtually no current flows. This current will be on the order of 1e minus 16 or less for a typical thyristor. With a very slow ramp at some critical voltage, this device will switch from a blocking state to an on state. This gives us what's called the S curve, where abruptly the current will rise up and switch from this off IV curve to this on IV curve. This fold back is due to series resistance to the device, and then he'll trace up the on state and saturate out at a fairly high current. This could be hundreds of microamps up here. When I turn around and come back the opposite direction, we're going to come down here, and he's going to follow this on state IV curve until I get to enough a low enough voltage and a low enough current that I can no longer sustain the connectivity of the device, and he'll suddenly drop from the on state down to the off state and then follow back here. Since there's these two unique states, off versus on, we can use that as a memory element where logic 1 is an off state where he won't conduct current. A logic 0 is an on state. If I come and do a read somewhere out here, I'm going to have maybe 6 orders of magnitude difference in off current versus on current in reading this device, which makes sensing the device in a circuit very, very simple to do.
So where do engineers run into problems when they're designing with memory? What's the typical problem that they're going to run into, and what do you have to keep in mind as you're moving forward?
With DRAM, scaling down as it is, they're storing the information in the DRAM as charge on a capacitor. This capacitor has to be large enough to give a large voltage swing on the bit line when charge is transferred from the capacitor back out to the bit line. The problem they're running into is they scale below 20 nanometer feature size. They've reached a point where they can't make the capacitor any bigger in capacitance at the same time where they're making the physical size of the capacitor get smaller. And so they're running into a roadblock where they're uncertain on how they're going to scale DRAM down into the deep sub 20 micron range. So what we're looking for is a solution here that allows us to continue to scale down where we're no longer dependent on having a large physical capacitor to store information. Here we can store the information as this latchback mechanism as on versus off connectivity rather than as charge stored on a capacitor. So this opens the door for us to continue to scale down.
And this has been one of the problems that people have been talking about, right, in terms of scaling memory, where you need to get that density because otherwise you can't handle as much data, you can't handle as much storage, but you also can't shrink it beyond a certain point.
That's correct. Here we can shrink because we have lots of on-off margin, we have lots of current even in a very small device. And so we see good scalability of this way down into the 10 nanometer range and even going below that.
How do we physically build it in silicon? What are we looking at now?
Well, what we want to do to build this thyristor is capitalize on the way geometries are built in silicon now in advanced MOS processes rather than the way they were building bipolar transistors back in the 1970s using lateral devices and very deep junctions and field oxidation. So what I've drawn here is a cross-section of what a string of these thyristor cells might look like in a modern semiconductor process. And what I've shown here is the surface of the semiconductor is here. These regions here are the shallow trench isolation that is being used currently in MOS devices. If we're willing to move the depth of this shallow trench isolation just a little bit deeper, then we can build this PN-PN structure inside of the gap between a shallow trench here and a shallow trench here. So what we're looking at in this is we're going to start off by building the shallow trenches here. We're through some doping mechanism, either epitaxial or ion implantation, we're going to put a deep buried N layer subsurface down here that doesn't go deeper than the shallow trench isolation. Then we're going to stick on top of that a P layer, again through a high energy deep implant, and stack on top of that a shallow N layer that with, again, a high energy implant. And finally, we're going to finish with the standard CMOS P plus source drain that would be used on a CMOS PFET. This builds this PN-PN structure that we were talking about in the other diagram. Now, this can be a feature size, this can be a feature size, so we end up at 2F for this dimension. When we rotate that 90 degrees, I end up at 2F and 2F. So now I'm down in the range of a 4F to 4.5F squared area for a cell, which is even smaller than what you have in current DRAM processes. The next challenge we have is lateral connection of this buried layer. We need to be able to connect this buried N layer to this buried N layer to this buried N layer to give a row or a column connection depending on how we choose to operate the cell. We're doing this here by, when we formulate this shallow trench, we're going to partially fill the trench, and then we're going to put in a metal connector layer that will go from this buried N layer to this buried N layer, and then fill the rest of the trench up with oxide. And so now what we have is the ability to have current through this cell flow down, then throw laterally across to, after some number of rows or columns, we'll have a vertical connection that is all N-type. All we've had to do is omit the shallow P layer here and use the N plus source drain implant mask on top. Now the current can flow out and into a wire that's up on top of the array.
So what does that do from a memory performance standpoint?
It makes the cell very small. Along with that, the cell ends up being very low in parasitic capacitance for both the wire that's connecting here and the wire that's connecting here, because the capacitance you're seeing through this cell is just the junction capacitance of this layer, these three layers, and those are three capacitors that are in series, which makes the capacitance even smaller. So it means I have low capacitance combined with a fairly high current carrying capability for the on state of the thyristor, which can give me very good sensing speed.
So the signal has to go less distance. It also can go through one layer versus another much faster than it could in the past.
Yes.
How about in terms of power? That's the other side of when you start stacking up die.
Okay. The big issue we have here in power is two issues. There's the read and write operating power, which the way we operate this cell is going to look very much like conventional memories. It's going to be word lines and bit lines that are toggling from VDD to ground or some percentage of that voltage. Standby power is very interesting in this device because in order to keep this device in the conducting state, we actually can use very, very little current to maintain that on state. So looking at this diagram, let's talk about the typical device in the memory, which is not being accessed, is just sitting here in what we call a standby state. I've shown how in this diagram where if I go higher than this voltage I call V hold max, the cell will trigger from the off state to the on state. Conversely, when I start to go this direction, at some voltage that I call V hold min, the cell will suddenly drop off of the conducting IV curve and onto the off state IV curve. I've labeled V hold min as the point where this drops, and what I want to highlight is what the current is through the cell at this point V hold min, and I call that I hold min. What we typically see on this device is this current, which will maintain the on state and hold the cell right here rather than letting it drop down to the other curve, is on the order of about 0.1 to 0.01 picoamps, which is a very small amount of current. If I were to compare this to DRAM in standby, DRAM, when he's in auto refresh mode in standby, is consuming about 2 picoamps per bit in power. We're talking about 0.1 or less, which is more than 10 times lower than the DRAM in standby operation. So we have a chance to have a much lower standby power on this chip. Where when we're in read and write operation, we're going to take the bit line up to a voltage up here for temporarily to read. We can move outside this window for short periods of time without the cell triggering, as long as we don't hold it there for a prolonged period and see this transition. Similarly, I can come down here below V hold min for short periods of time, hundreds of nanoseconds, without the cell being lost because it takes time for this transition to occur.
And that's one of the unknown or lesser known features of DRAM, right? Is it leaks, and you really do have to refresh it all the time.
Yes. So DRAM uses a MOS transistor to transfer charge from a bit line to a capacitor. Then you turn off the MOS device and let it sit there, storing that charge on the capacitor. Well, we all know that MOS transistors have leakage. They have subthreshold conduction leakage, which in advanced nodes tends to get very large. They have diode junction leakage. They also have tunneling leakage through the gate oxide. All of those mechanisms slowly leak away the charge on that capacitor in the DRAM, and you can only let it go down so far before you have to come back, sense what's in there, and then write it back in to refresh it back up to the full charge condition. In the operation of the thyristor, that operation all goes away. As long as I hold the bias across an unselected cell somewhere between V hold min and V hold max, that cell will retain his on state indefinitely. He will also retain his off state indefinitely. And as we've shown, if I can put it near this point, not only will it hold it indefinitely, but it will hold it at an extremely low power level.
And most people, when they're designing systems, tend to think of the leakage in terms of the logic and the rest of the SoC. They don't necessarily think in terms of the memory. How significant can that be?
Oh, it's tremendously significant. This is true in DRAM. They're having a much harder time as they're scaling down, maintaining the 64 millisecond refresh period that's holding because the leakages are getting worse. It's also true in SRAM. As they've been scaling the SRAM devices down, the leakages through the MOS transistors in the 6-transistor SRAM are getting significant, both from a power point of view and from the impact they have on the stability of data in the cell when they're doing read and write operations. So operating in the thyristor mode, many of those problems go away.
What are you trying to do here?
Okay, so this is an illustration of how we operate an array of these cells. We are doing this in what is termed Crosspoint Memory architecture. You are aware of the products that are being offered now by Intel and Micron in the 3D Crosspoint and so on. We're doing a similar type approach for operating this array. So what I've shown here is 2 rows and 2 columns as a representative of a much larger memory array. So we would continue more rows this way, more columns that way. I'm going to have a row that I might want to select, a row that I would leave deselected. In standby operation, what we want to do is bias all of these cells in the array at that point we showed on the IV curve diagram near V hold min. Now here's how we're going to do that. In standby, we're going to hold these bit lines all at VDD. We're going to take these transfer gates to the rows and turn all of them on simultaneously, which will connect all of these row lines to this wire here that's going to go down to a current source. The value of this current source is going to be set at the minimum holding current for the individual device, as we showed in the IV curve, times the number of cells that are going to be in this array. So what's going to happen is this current is now going to get distributed among all of these cells at their individual I hold min. Now we're going to have to guard band this value somewhat to account for variability inside the array, maybe 2x or 3x on that I hold min current.
Why are you using a current source rather than a voltage source?
Okay, that's a very good question. Remember on the IV curve that we looked at earlier, the current scale on that was log of current. It's a semi-log plot. So for a very small change in voltage this way, I'm going to get a very large change in current through the cell. Well, if I try and design a voltage regulator to hold this at the exact voltage I need, I'm going to have to control that voltage to within a few millivolts, or I'm going to see very large variations of the current through the array. If we turn this design problem the other way around, and I provide the amount of current that's needed with a reasonable guard band, then what happens is all of these cells in parallel will automatically bias themselves at the correct voltage in order to support this current flow that is adequate to maintain all of these cells in the on state. And so we have much more precise control of the standby power this way.
So how do you do a read on this?
Okay, a read operation in this array is going to occur very similar to what you have in an SRAM. So what we're going to do is we'll take these bit lines at VDD and then float them. Then on the selected row, we will turn this pass gate to the off state and instead come in and have our row decoder drive this signal from this holding voltage to ground. When we do that, this bit line that was left floating at VDD and this node at ground are now going to put a voltage bias across this cell of VDD. If this cell is on, he's now going to be able to conduct many microamps, tens or more microamps of current in this direction, which is going to take this floating bit line and cause him to fall, just like you would see in a normal SRAM or in a DRAM. Conversely, if this cell is off, what's going to happen is his current capabilities now, as we said before, on the order of 1e minus 16. It's way too low to discharge the capacitance on this bit line at any reasonable speed. So this node is going to be left floating high near the VDD level. So all I have to do to sense whether I have a 0 or a 1 in this cell is look for the change in voltage on the bit line. That's a function of the current that flows through the cell. If I look at this row, because he's still connected to this line, is going to be sitting at approximately V hold. This bit line, this memory cell in the upper right-hand corner is seeing VDD and V hold, which is going to give us currents on the order of 1/10 of a nanoamp, which again is too low a current, even with many, many cells on this column, to accidentally discharge this guy and cause a false sensing of an on state. Over here is we have the same condition initially, V hold across this cell. As this bit line falls, that voltage collapses. We'll actually go below V hold min, but we're only going to do this for a few nanoseconds or so. The cell will tolerate that and still stay in his on or previous on or off state before we come in and pre-charge him back high again. So that's the mechanism in which we can isolate the cells that are on the selected row from all of the cells that are on the non-selected column without having to have an access transistor in addition to the thyristor to form this memory cell. And that's the key to making this very small, is not having to use an access transistor.
So we've addressed read. How do we do write?
Okay, to do a write operation, what we're now going to have to do is take the memory cell and get a larger voltage across the selected cell in order to do a full write 0 or turn from off to on. So what we're going to want to do there is actually a very similar operation on the bit line. We're going to leave this bit line floating at near a VDD level, but when we come in and disconnect this row from the holding voltage and back to the driver, what we're going to do is we're going to drive him down to a voltage less than ground. Or conversely, we could come and raise the pre-charge voltage on the bit line such that when we try and turn this cell from off to on, the voltage we're going to put across here is going to be quite a bit larger than the V read voltage. And that will be enough to cause this cell to transition to the off state quickly rather than over a very long time. So in order to keep this isolated, when we take this guy at a lower voltage, if we look at this cell, which we don't want to program, if he was in an off state, then what I'll do is I'll physically pull this bit line down before I apply the pulse on the word line to minimize the voltage drop across this cell. So that would mean taking the columns we don't want to write and moving the bit line down in a pulse and then bringing them back up when we're done. And that'll give me a reduced voltage across here that would avoid accidentally turning this cell from an off state to an on state.
One other side of this is, how do you do a write state to the off state from on?
Okay, to move to a cell from on to off, we now have to move to the left side of that IV curve where we reduce the voltage drop across the cell. The further we go below the V hold min value, the faster we are going to be in shutting off the cell and converting him to the on state. So let's look at how we would do that. Let's assume that this is the cell that we want to switch from on to off. What we will do is take this bit line, and as we talked about before for the unselected case, we'll bias him low. We might take him all the way down to ground. We'll take this word line, and instead of pulsing him low, we'll pulse him high, perhaps to VDD. When we do that, what we end up with is minus VDD across the cell, an actual negative voltage of about -1, 1.2 volts. That's going to very quickly cause this cell to transition from the on to the off state.
So what happens to the other cells? You've got 3 other cells sitting there.
Okay, so now we have to look where this is going to pulse positive. We don't want the voltage across this cell to go negative, so if we've left him up at VDD, rather than bringing him down, then the voltage across this cell will go to something like 0 volts, or less if we don't take him quite all the way to VDD. That will make, from a time point of view, this cell very slow to switch from an on to an off state, whereas this cell switches very fast. So if we keep the right pulse short, this cell doesn't get disturbed while this cell still gets selected for write. Now we have to come and look at this case. We've got this guy at V hold. We're taking this guy down to perhaps ground. Well, that'll put him down at something like -0.7 volts. If we were to be pulsing this guy, maybe not at ground, but say to plus 0.4, then the voltage drop across this cell would be something like -0.3 volts, which, just like here, is too slow to disturb this cell in the amount of time allotted. So we end up isolating just this cell for writing, and this cell are still in a non-selected state from a write perspective.
So Bruce Bateman, thank you very much for a great explanation. A lot of people take memory for granted. They think it's memory is memory. The reality is it's really not.
It's interesting because if you look at many of the SoCs that are being manufactured today, up to 60 to 70 or maybe 80% of the area on those chips is memory, and only 20 to 30% of it is logic. And so that memory is a very, very important component.